Lesson 952, One-Way ANOVA, Unequal Sample Sizes. We finished Module 9 with a continuation of the previous section by continuing to look at ANOVA. In our introduction, dentists use metal alloys to make fillings. Many metals, such as pure gold, are too soft to use for fillings, but they can be hardened by adding other metals at different melting temperatures to make alloys. Researchers used 3 different methods to make gold alloys for dental fillings. Vickers hardness numbers are recorded for samples of each method below. A Vickers hardness number is a measure of the material's hardness. The higher the number, the harder the material. For example, diamonds are extremely hard and have a Vickers hardness number of 10,000. So here we have 3 different methods. And there's all of the Vickers hardness numbers for those 3 methods. Number 1 asks, can we use the methods of one-way analysis of variance described in the previous lesson to test for equal mean hardness using the data above? It might be a little bit difficult to see, but if you were to go through and count up all of the different sample sizes for those 3 methods, you'd see that the sample sizes are not the same. So the answer for number 1 is actually no, since the sample sizes for each method are not equal. So, in this lesson, we expand the previous discussion of one-way ANOVA to the case where sample sizes are unequal. The assumptions for one-way ANOVA continue to be that samples are random and independent and are drawn from each of k populations that are normal with equal variances. The test is robust, meaning that moderate departures from these assumptions still yield fairly reliable results. We will use these data to test the claim that the mean hardness number is the same for each alloy method at a 5% level of significance. So here we are going to do a hypothesis test, and the claim is that the mean hardness number is the same for each method. Step 1. Determine the hypotheses. In the previous lesson, we learned a method known as one-way analysis of variance, or ANOVA, to test the null hypothesis that the means mu1, mu2, mu3, etc., all the way up to mu k, are equal against the alternative hypothesis that this is not true. So number 2, give the null and alternative hypotheses using words in context below. If you think about the idea of the null hypothesis that we've seen now for 3 modules, it means that nothing has changed. Things are equal. So, in the null hypothesis, we would say that all 3, since there are 3 of them here, all 3 methods will be the same. So all 3 mean hardness numbers is the same. The alternative hypothesis has to be an alternative to that. And in our case, if you remember what we saw in the previous section, all we need is one of them to be different. So for the alternative hypothesis, at least one mean hardness number is different. Number 3, give the null and alternative hypotheses using symbols below. We can really only do this with the null hypothesis, where we can say mu1, the mean hardness number for method 1, is equal to mu2, the mean hardness number for method 2, and equal to mu3, the mean hardness number for method 3. The alternative hypothesis would actually just be exactly the same as we wrote for number 2. So if you want, you could just draw an arrow. Those 2 are both going to be the same. Step 2, collect the data. Number 4, the sample mean, standard deviation, variance, and sample size for methods 1 and 3 are given below. Fill in the corresponding values for method 2. We will keep 2 places after the decimal as we proceed. So this is just like what we saw in the previous lesson. We're going to want to go to our calculator and input all of these numbers into 3 different lists. So I'm going to go to the calculator and I'm going to show you the lists that I have. So I press the Stat button and Edit. I've already entered my data into lists 1, 2, and 3. So method 1 is list 1, etc. And if I go all the way to the bottom, you'll actually see why we can identify that the sample sizes are different. List 1 or method 1 has 30 pieces of data. You can see from the calculator. That's why in the workbook it says n equal 30. If I go over to list 3, you can see that there's 27. That's why it says n equal 27 for method 3. So for list 2, I can see that there's 25 pieces of data there. So I can write n equal 25 right here. But of course, don't forget we can use one variable statistics. So stat, calculate, one variable stats, and I'm going to use list 2 and calculate, and I can write down x bar, the sample mean for method 2. That's 804.84. And then for the standard deviation, notice there I have capital SX, so that's 97.02863838. And to get the variance, I have to square that. So I'm going to take that whole number that's there and square it, and then I'll round that answer to 2 decimal places. So S squared, we will say, is 9414.56. We're going to need those 3 lists in a little bit, so we'll come back to the calculator after we've done a few other problems. So number 5. In the image below, confidence intervals are depicted graphically for the mean hardness for each method. Write a sentence or 2 describing what this tells you about the apparent differences between the corresponding population means. So if we look at this confidence interval, think back to a previous lesson where we saw the differences in medication. We can see that the mean, which would be the center of these confidence intervals, they are definitely in different places, and one of them, for method 3, is certainly much more different from the other 2. We can also verify that with the data in the table above. But also we can see that the confidence interval for method 3 is much lower than that for method 1 and method 2. So we could see that the mean hardness for method 3 seems to be less than the mean hardness for the other 2 methods. And of course, this is all just based off of this data, but we can at least say that. So then step 3, assess the evidence. To conduct the test, a sample is drawn from each of the K populations. When the sample sizes are all equal, the F-statistic uses 2 different estimates of the variance sigma squared that is common to each of the K populations. So this is just like in section 951, capital F is equal to the ratio of the variance between the samples and the variance within the samples. When the sample sizes are not all equal, these variances become more complicated. Variance is the square of standard deviation. We have seen the formula for standard deviation before. This, in fact, came from module 2. If you were to square both sides of that formula, you end up with the next line, S squared equals, and that says the sum of the quantities x minus x bar squared divided by n minus 1. The variance between the samples uses S sub x bar squared, the variance of K sample means. And that formula, written just below, says S sub x bar squared is equal to the sum of the quantity x bar minus x double bar squared divided by K minus 1. So that's a new symbol, x double bar. And you can see right below, in this formula, K is the number of samples, and x double bar is the grand mean, which means a weighted mean of the sample means. The formula for that calculation is right here. X double bar is equal to the sum of n times x bar divided by capital N, where capital N equals the sum of n, meaning the number of values in all samples combined. So if you added up all of the sample sizes. A weighted mean is one which assigns weight to values based on the sample sizes. Weighting is important since larger sample sizes are more reliable. We can update the variance between the samples by moving the variable sample size into the sum, which is the variance of the sample means. So here, sigma squared can be approximated by n times s sub x bar squared, which is equal to n times that formula that we had for s sub x bar squared up above. And then what they were saying is we can move the n into the formula, so we get the fraction sum of the products n times the quantity x bar minus x double bar squared divided by k minus 1. So number 6, compute the grand mean using the table below. The mean and sample size for method 2 are missing, so we're going to go back and write in what we said the mean was, which was 804.84. And then n, the sample size was 25. So then we need to multiply n times x bar, so 25 times 804.84. That gives us 20,121. And then we have at the bottom here a total, which means we have to add up the column numbers, so 23,817 plus 20,121 plus 19,450.8. And that gives us 63,388.8. So then the grand mean is taking that sum, 633,88.8, and then dividing by capital N. Remember, capital N is the total of all of the sample values, so 30 plus 25 plus 27. You can write that in the chart up above as well. That would be 82. So then if I take 63388.8 and then divide by 82, I get approximately 773.0. We could go out a couple of more decimal places, 773.034, but we're going to stick with 773.0 just for the purposes of what we see in the following couple of charts. Also, just make a note at this point, these calculations are all going to be done by the ANOVA function. So we're going to do number 7, 8, and 9 on the next page, but then I'm going to calculate everything using the ANOVA function and finish the rest of the lesson with that. So if you're starting to feel a little bit overwhelmed by these calculations, everything's going to be just fine. ANOVA function is going to take care of all of that. So continuing on to the next page, the numerator of the variance between the samples is often referred to as the sum of squares between the samples, which means SS for sum of squares with a subscript between. And all they are saying is the numerator that we had before, which was this expression, that is SS between. So number 7, compute SS between using the table below. So here we need to fill in again what we had on the previous page. Method 2, n was 25. X bar was 804.84. And then we need to calculate this to fill in the next blank in the row for method 2. So I actually want to write that out a little bit. So first of all, for method 2, n is 25. X bar is 804.84. And then we need to subtract the grand mean that we had on the previous page, which was 773. and then we need to square that. So I have to do the subtraction first. 804.84 minus 773. So this becomes 25 times 31.84. And then I have to square that and then multiply by 25. So this becomes 25344.64. And that's what gets entered here for method 2. 25344.64. There's actually a couple of typos in what they have written here, so I'm going to change those. If you were feeling adventurous and you wanted to calculate these on your own, for method 1, you should actually get 13104.3. And for method 3, you should actually get 74702.5. So now I'm going to total those. So I take what I have for method 1, 13104.3, plus 25344.64, plus 74702.5. And when I add those, I get 113,151.44. That becomes SS between. And I want you to keep in mind that abbreviation SS. We're going to see that with the ANOVA function in just a little bit. Continuing on, dividing SS between by its degrees of freedom, k minus 1, gives the variance between samples a mean of the squared deviations between the sample means and the grand mean. This is abbreviated MS between, which means we take the result that we had before for SS between and just divide by the degrees of freedom, k minus 1. Number 8, MS between is a measure of total variability among the sample means. If the null hypothesis is false, will MS between be larger or smaller? So here we want to think, if the null hypothesis is false, will the total variability among the sample means be larger or smaller? Just think, if the null hypothesis is false, it means you don't have an indication that the mean hardness numbers are all close to each other or not different from each other. So that means that you would have a large amount of variability. They would be differing from each other in a large way. So we would expect a larger amount of variability. So number 9, compute MS between by dividing SS between, the answer we got for number 7, by its degrees of freedom. So I'm going to take 113,151.44, and I have to divide by the degrees of freedom, k minus 1. And they say, remember, k is the number of samples. We have 3 methods, which means we have 3 samples. So I have to divide by 3 minus 1, or 2. So take 113,151.44 and divide by 2. So if you do that, 113,151.44 divided by 2, you get 56575.72. Okay, so here's where I now want to switch over and take a look at the calculator function, so we can do these calculations that we just saw and then finish the rest of this lesson in a much easier way. So back on my calculator, I'm going to press Stat. I already have my data in the lists, so I'm going to go over to Tests and then go all the way to the bottom. You can also do that by just pressing up once, and you get to ANOVA. Press Enter, and then I need to just type in second and 1 for list 1, comma, second and 2 for list 2, comma, second and 3 for list 3. And then press Enter. And right here, we've seen how we've used this before. There's our capital F. We know that's going to be a big result at the end of this whole exercise. There's P, our P value, also going to be important. Now take a look at what's written right below. Here we can see it says df equals 2. That's the degrees of freedom you just used in number 9. Right below that, it says SS equals 113,235.595. If you take a look at what you wrote in number 7, you had 113,151.44. So from our calculator, we actually got something that was close to that. Why is there a difference? Our calculator didn't do any rounding. We had rounding throughout a lot of these calculations. So I'm just going back to the workbook, and for number 7, I'm saying for our calculator, we got SS1, that's the first SS that we can see in our screen, is 113,235.595. And then you can also go down. MS between, the answer for number 9, that's MS1. Take a look at your calculator. You have 56617.7975. In what we got for number 9, we had 56575.72. So they are close to each other. There's a difference again because our calculator didn't do any rounding. So on the workbook, I'm writing for our calculator result, we got MS1, the first MS that shows up. That is 56617.7975. So now if you think about what we're about to do next, we're going to do some other things in calculating the F statistic. We have all of that here on our calculator. So I'm going to jump back to the workbook, picking up right below number 9. It says the denominator of the F statistic estimates the common population variance, sigma squared, using the variance within the samples. When the sample sizes are different, this is the weighted mean of the sample variances, using the degrees of freedom n-1 as weights. So here is what we saw actually in a previous lesson. S sub p squared is equal to the sum of n-1 times s squared divided by capital N minus k. The numerator of the variance within the samples is the corresponding sum of squares, SS within. This is going to be SS2 from the ANOVA function. So number 10 says compute SS within using the table below. You can certainly do that, but we are just going to go to our calculator, SS2, and if you go back to your calculator, the second SS value that you see there is 1086090.36. The degrees of freedom for SS within is the sum of the degrees of freedom for each variance that it uses, in this case capital N minus k. But what we are just going to notice is that there's a second degrees of freedom sitting right there on our ANOVA screen. So in this case, this is just df2, which you can see your calculator says 79. The variance within the samples is the mean of squares within the samples, MS within. This is SS within, and meaning the second SS number, divided by its degrees of freedom. So again, you could calculate this by hand, but this is also just MS2 that's sitting there on your calculator, and that's 13747.9792. And of course, we could round that if we want. I'm just writing down what my calculator says. As before, the F-test statistic is the ratio of the variance between the samples, MS between, and the variance within the samples, MS within. So MS1 divided by MS2. Again, you could do that division on your own, but number 12, asking for the F-test statistic, again, go back to your calculator, and at the very beginning, you see it says capital F, and what's written there is 4.118. And again, just like we saw in the previous lesson, that becomes a big point. We really just want that F-test statistic. Everything else led up to that. So now both MS between and MS within are estimates of the common population variance, sigma squared, computed under the assumption that the null hypothesis is true. In this case, the estimates would be similar and the test statistic should be close to 1. But as we can see, our MS values are definitely different. And when we did our division, we got something that was bigger than 1, 4.118. So number 13, will the F-test statistic tend to be larger or smaller if the null than 1 if the null hypothesis is false? How does this affect whether the F-test is right-tailed or left-tailed? This is exactly like what we saw in the previous lesson. If the null hypothesis is false, we would expect to see the F-test statistic to be larger than 1, and this means we're going to have a right tail. So F will be larger than 1, and we would have a right tail. For this test, just like lesson 951. Number 14, write the value of the F-test statistic on the image below. So again, TS, that's our test statistic. This was 4.118. And then below number 14, they just remind us of those degrees of freedom values. So number 15, write down our degrees of freedom. We've already done this. DF1 we said was 2. DF2 we said was 79. And then again from our calculator, we don't need to use their website. We just have it on our calculator on our own. We get 0.0198, but that would actually round this to 0.020. That becomes our p-value. So now, just like with any hypothesis test, we start drawing some conclusions. So number 16, make a decision about the null and alternative hypothesis. If you go all the way back to the beginning of the lesson, you'll see that our significance level that we had was 5%. So we said that alpha was 5% or 0.05. Our p-value is 0.02. And that is less than alpha. Because the p-value is less than alpha, that means we reject the null hypothesis. And then that means that our data supports the alternative hypothesis. Continuing with our conclusions, number 17, write a conclusion to the hypothesis test in the context of this problem. So if our data supports the alternative hypothesis, think about what that means with your claim. If I go all the way back to the beginning of the lesson, remember that our claim was that the mean hardness number is the same for each alloy method. So the claim in this case, here's an example where the claim was the null hypothesis. So we would say that the data does not support the claim that the mean hardness number is the same for the 3 alloys. That's what we could say for number 17. The data does not support the claim, since that's what they said the claim was, the claim that the mean hardness number is the same for the 3 alloys. You could also say the data supports that there is a difference between the 3 methods. Again, you can put this into context, but I just went back to their wording and used that. Number 18, is there a mean hardness level that stands out as being particularly different? Again, I would just say, based off of the confidence interval graph that we saw, we can see that method 3 seems to be the most different. And then finally, number 19. If a harder alloy is better, what does this tell us about the alloy that stands out? If no other factors influence the decision, should dentists use or avoid this alloy for gold fillings? Again, we noticed that method 3 had estimates from their confidence interval that was lower than the other two. So lower would not be better. So dentists should avoid that alloy. The secret word for this lesson is diamond. You need to know, when conducting a test comparing k equal 3 or more means using one-way ANOVA with unequal sample sizes, the null and alternative hypotheses are H0 for the null hypothesis. All of the means are equal, so mu1 equals mu2, etc., all the way up to mu k. And the alternative hypothesis is at least one mean differs from the other. The test statistic is this ratio, ms between divided by ms within. And again, based off of our calculator, this is the first ms value, ms1 we can call it, divided by ms2, the second ms value that comes up on our calculator. There's those formulas. You aren't going to need those formulas, and you won't even see them printed on the test because we don't need them. What we need is just our calculator function. Below those formulas, you can see what those symbols stand for, but again, keep in mind everything that we've been using our calculator for. So what finishes this lesson is another example. And so here we have 5 lists. You can see that the sample sizes are different. You can see that you're asked to state the null and alternative hypotheses, the degrees of freedom. You're asked to write down SS, DF, and MS values. You know how you can do that by just going through your calculator. And then you're asked for the test statistic, the p-value, and then you're asked to draw some conclusions. This is a great example for you to do on your own. Work with your group members, even though you aren't all sitting at the same desks. You can talk to each other on the phone. You can also come into your chat sessions with your instructors and ask about it there. Something that I want to point out for the take it home, you have a couple of other different tables here. If you get to a point with your calculator where you're running out of room, try to go through and delete some lists. You can also add lists just by going onto the edit screen and just moving over one column past list 6 and just create a name for a new list. So you can do that for the take it homes if you need to.